Every year, more than 50,000 tons of uranium are mined across the globe. But to extract just a few grams of its energy, mountains of rock must be moved. It's a journey that begins in a desert where the temperature hits 38 degrees Celsius and ends inside a reactor that powers New York City. It involves centrifuges that spin faster than a jet turbine and chemicals that can dissolve metal in seconds. But the most interesting part is something that even the safety manuals don't mention. Watch until the end and you will learn a secret that will change how you think about nuclear power forever. It all begins in the dust, literally. Uranium ore is mined in hot, arid regions: Arizona, Wyoming, Texas, New Mexico. Here, the sun is relentless, reaching 38 degrees Celsius in the shade, if you can find any. There are two main extraction methods: open pit mining, where the topsoil is stripped away, and underground mining, with explosives and hoists. There is also a third, more subtle technique: in situ leaching. Pipes are drilled deep into the earth. Special solutions are pumped down to dissolve the uranium directly from the rock, and the resulting liquid is then pumped back to the surface. The ore itself, a grayish-brown rock, looks unremarkable, but within it, the crucial isotope uranium-235 makes up just 0.7%. The rest is a vast, almost useless mass that is inert in a reactor. And to squeeze the required drop of energy from it, hundreds of tons must be processed. After mining, the ore is crushed, milled into a fine powder, and thrown into a chemical bath of acid or alkaline solutions. This is followed by filtration, precipitation, and drying at 260 degrees. The final product is yellowcake, a bright yellow uranium concentrate. Officially, it's known as uranium ore concentrate, but everyone at the plant just calls it yellowcake. It looks striking, a mustard-colored loose powder like a spice for a barbecue. But this is a substance you must not touch and must never inhale. It emits alpha radiation, has a long half-life, and its dust is dangerously toxic. The yellowcake is sealed in double-walled drums, loaded onto escorted trailers, and plastered with radiation warning signs for the journey to the enrichment facility. This is the start of the path that turns a poisonous dust into the clean white light from a lamp over your kitchen table, or the electricity that powers the tube deep beneath London. Right, the yellowcake has arrived. It's radioactive, dry, and sealed in its drum. The next step? Turn it into a gas. And not just any gas. This is uranium hexafluoride. The uranium concentrate is first dissolved in acid, purified, and converted into uranium dioxide. And here, the alchemy begins. The uranium dioxide is treated with fluorine gas in special reactors at 540 degrees. The reaction creates a volatile, transparent gas that boils at just 56 degrees. A little heat, and it turns from solid crystals into a vapor. But it's not that simple. This gas is extraordinarily toxic. It corrodes most metals, destroys human tissue, and on contact with humid air, it instantly transforms into hydrofluoric acid and uranyl fluoride, a lethal cocktail. That is why this entire process is conducted inside sealed, automated reactors. The substance is stored as solid, whitish crystals, formed by cooling it to room temperature. These crystals are kept in steel cylinders, each engraved with a serial number and a radioactive symbol. A single cylinder weighs almost 14 tons. You think your washing machine spins fast? You haven't seen a nuclear centrifuge. They can reach 70,000 revolutions per minute, more than 10 times faster than a jet engine turbine. And all for one purpose: to separate uranium isotopes. Uranium hexafluoride, that toxic gas we just created, is fed into a tall, narrow cylindrical chamber, which is then spun at an insane speed. Centrifugal force does the work. The heavier uranium-238 atoms are flung towards the outer wall, while the lighter, crucial uranium-235 atoms remain closer to the center. But one centrifuge isn't enough. They are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas and passes it to the next. This process is repeated, cycle after cycle, until the concentration of uranium-235 reaches at least 3 to 5%. This is the standard grade for reactor fuel. Okay, the gas is enriched, but you can't feed a reactor with the gas. So now it is converted back into a solid, this time a ceramic form. After a series of chemical reactions, the gas becomes uranium dioxide powder, a dark gray solid. This powder is pressed under 20 tons of pressure into small cylindrical pellets, just 8 millimeters in diameter. They look almost harmless. Next, the pellets are sintered in a furnace at nearly 1650 degrees, making them as hard as porcelain. They are then polished and ground to precise dimensions. The finished pellets are loaded into long metal tubes known as fuel rods, typically made of a zirconium alloy because it resists corrosion and can withstand intense radiation. Each rod holds over 300 pellets. The rods are hermetically sealed and then bundled together into modules called fuel assemblies. They look like a square frame holding a grid of several dozen rods. A single assembly can weigh over 680 kilograms and will operate inside a reactor for up to 6 years. The finished fuel is packed into armored containers for transport. The journey is made under guard, on a special route with a security escort and GPS tracking. Left over from all of this is the depleted uranium hexafluoride, known as tails. It's a mix of isotopes with a small amount of U-235 remaining, but not enough to be useful. These tails are stored in steel cylinders at designated secure sites. When a fuel assembly has served its 4 to 6 years in the heart of the reactor, it is no longer a shining star. It is removed by a robotic system and moved into a deep pool of water, over 6 meters deep. The water cools the assembly and shields the intense radiation because the fuel is still incredibly hot. It rests there for several years. After that, it has 2 possible futures: long-term dry storage in concrete and steel casks, or reprocessing. This usually happens in other countries, as the US and UK primarily store their waste rather than reprocess it. In a dry storage facility, the assemblies stand for decades, cooled by natural air convection, as if in a nuclear monastery. This isn't the end, but a new phase of life. A slow, controlled existence, but one deeply connected to the future of energy. Because even after its time in a reactor, this fuel remains a source of heat, a lesson in engineering, and a reason for profound respect. Imagine a river of white-hot metal, as bright as the sun, born inside a giant furnace, melting everything in its path. But did you know that to create 1 ton of iron, you need almost 2 tons of rock and coal? It seems like alchemy. Hundreds of kilograms of oxygen and impurities vanish from dirty ore, leaving only pure metal behind. In the US, just a handful of these furnaces produce over 25 million tons a year, enough to build 250 aircraft carriers. And yet, there is a secret hidden within this story, one that will only be revealed to those who watch until the very end. It all begins deep in a quarry, where iron ore is mined. This isn't metal, but reddish-brown rock that looks like rusty earth. The iron is tightly bonded with oxygen, and the primary mission is to break that bond, liberating the metal within. Along with the ore, two other key ingredients for this infernal recipe arrive at the plant. The first is coke, a specially processed form of coal. It's baked in an oxygen-free oven to remove all impurities, resulting in pure, porous carbon that burns with incredible heat. In our process, coke is both the fuel and the main chemical agent. The third ingredient is limestone, a common rock. Its role? It's the cleaner. When heated, the limestone will act as a magnet for all the waste, collecting it into a separate mass. Now, let's go to the plant to meet the hero of our story, the blast furnace. It's a tower over 30 meters high, lined entirely with fireproof brick and wrapped in a network of pipes. This tower never sleeps. It runs continuously 24 hours a day, sometimes for years without stopping. It is a giant stomach that must be constantly fed. From the top, using a special skip hoist that looks like a small rail car, our ingredients are charged into the furnace. Not just thrown in, but layered like an industrial lasagna. A layer of coke, then a layer of iron ore and limestone, another layer of coke, and so on. To get 1 ton of liquid iron, you need to load almost 2 tons of raw material into the furnace. This figure includes the iron ore, the coke, and the limestone. It shows just how efficiently a blast furnace works as a giant filter. It takes nearly 2 tons of rock and coal, burns away everything unnecessary, and yields 1 ton of pure, concentrated metal. This is true industrial alchemy. Once the furnace is fed, the heat is turned up. At the bottom of the furnace are special nozzles called tuyères. Through them, air is blasted in under immense pressure, superheated to 1100 degrees Celsius. This hot blast ignites the coke, causing it to burn with incredible ferocity. The entire mass of materials loaded from the top begins its long journey down through zones of increasing temperature. First, in the upper section, hot gas is rising from below dry and preheat the ore. A little further down, the chemistry begins. The burning coke reacts with oxygen to form carbon monoxide. And this carbon monoxide is our master thief. It greedily rises, meets the iron ore, and starts stripping away the oxygen atoms, leaving pure iron behind. About halfway down, the temperature becomes so intense that both the iron and the impurities begin to melt. This is where our cleaner, the limestone, comes into play. It decomposes and starts to bind with all the unwanted elements, forming a light molten mass called slag. At the very bottom of the furnace, in its heart, known as the hearth, a lake of 2 unmixable liquids forms. At the very bottom, being heavier, lies the pure molten iron, and floating on top, like oil on water, is the lighter molten slag. Every few hours, it's time for the tapping. A special machine, like a huge drill, pierces a hole in the fireproof lining of the furnace, first for the slag. A thick, bright orange river of molten rock erupts with a hiss. Once the slag is drained, the main event begins. The drill opens another hole slightly lower down, the iron notch. And from there, with a roar and a blinding glare, a torrent of molten metal is unleashed. It isn't orange, it's a brilliant white gold, so bright it's painful to look at without special glasses. The heat radiates from it, a physical force you can feel on your skin from dozens of meters away. This dazzling river of metal, throwing off fountains of sparks, flows down a long refractory channel into a huge mobile ladle shaped like a giant cigar on wheels, known as a torpedo car. This torpedo can hold several hundred tons of liquid metal and, like a thermos flask, keeps it hot while it's transported to the next stage. What we have created in the blast furnace is called pig iron. It contains a lot of carbon, which makes it very brittle. When the metal cools in the molds, it solidifies. After the mold is broken, a finished cast iron product is revealed. And so, from a cold, red rock through the fiery stomach of the blast furnace where chemistry and heat work their magic, this heavy, reliable, and durable material is born, ready to serve us in our daily lives. Each year, blast furnaces in the United States produce roughly 30 million tons of iron. It's a number so vast, it's hard to comprehend. Let's try. The average Nimitz-class aircraft carrier weighs about 100,000 tons. This means that in 1 year, American plants produce enough iron to build a fleet of 250 of them. Or to put it in more grounded terms, if we take the weight of an average passenger car, that's enough metal to make over 12 million vehicles. An entire automotive nation born in the fire of the blast furnaces in a single year. There are only about 15 blast furnaces currently operating in the entire country. We are not talking about thousands of small plants, but a small number of true titans. This means each of these towers is an incredibly productive monster. The average blast furnace in the U.S. produces over 5,000 tons of iron every single day. Over 90% of all pig iron produced in blast furnaces is not the final product. It is just the first step. This hot, carbon-rich metal is essentially the raw material for making steel. It is transported in torpedo cars to the next plant, where, in oxygen converters or electric furnaces, the excess carbon will be burned off, turning brittle iron into strong, ductile steel. So these 25 million tons of iron are the foundation from which skyscrapers will rise, bridges will be built, and cars, ships, and even simple tools will be made.